Okay, thank you for the invitation to give a talk here. It's very nice to be in KITP. So today I'm going to be talking about some work which is in collaboration with these wonderful people, Pranay Gorankla and Shuheng Xiao. And this paper came out last year, and then I'm very excited to share some sort of ongoing work with Orko Chatterjee and Dachuan Lu. So before I begin, I feel obligated to start with this slide. And now it's not because I'm following a trend. I wanted to actually point out that last year at Symmetries at Oxford, I had this diagram, and I actually had 4 circles. So actually, beyond high energy mathematics and condensed matter, I also want to point out that there's also quantum information, which plays a huge role in what I'm going to be talking about today. And so roughly in these 30 minutes, I'm just going to, this is sort of the time trajectory. I'm going to start from the Ising model, very simple stuff. Talk about gauging a bit, and then I'm going to go into this quantum information / mathematics land, talking about something called ZX calculus, and eventually get all the way to Hopf algebras. And hopefully I'll make it back in time such that I can talk about some generalized version of the Ising model based on these Hopf algebras. So the motivating question I want to ask today is, suppose I want to realize some symmetry, let's say categorical symmetry, in 1 + 1D on the lattice. And I want to demand that I'm in a tensor product Hilbert space. So when can I do that? And it seems that in the literature, we seem to already know how to do that if the symmetry is invertible, or in some cases, suppose your symmetry is the representation of some Hopf algebra. It seems we also know how to do that. There is some matrix product operator which we know how to write down. But it seems that generalizing beyond this has been a little subtle. So there seems to be, what is the current compromise we have? What's preventing us from doing that? One is that it seems that when we try to write down these operators, the Hilbert space that we try to write it down is not a tensor product. For example, you can write down these non-invertible symmetries on the anion chain, but the Hilbert space is not tensor product. Yes?
Do you also want to require that the symmetry is on-site?
Oh, no. So non-invertible symmetries, well, okay, depends on what you mean by on-site, but I just mean for a matrix product operator, it's already like, you cannot factorize it in that sense, yes. Yeah, so invertible could be anomalous, right? And I can still realize in a tensor product Hilbert space. Yeah. I'm only demanding something about the Hilbert space itself. Okay. Now, in this anion chain, the Hilbert space does not factor as a tensor product Hilbert space. You can try to lift that to a larger tensor product Hilbert space, but something weird happens. For example, some people found that the trivial object does not act as the identity on that Hilbert space. So that's something weird that can happen. Another way to resolve this is it seems that although we are speaking about symmetries in the IR, we can lift that to a symmetry in the UV. But this symmetry somehow mixes in an interesting way with lattice translations, and that has appeared recently. This is going to be what I'm going to try to pursue and sort of try to generalize. Now, the way to generalize this comes from the viewpoint of performing a so-called duality transformation. Now, I know this might not be a politically correct term, but let me stick to this terminology for now. For me, a duality transformation is just trying to view a same system in a different angle, right, which can offer some insights to its properties. For example, you might have a description A of describing something which looks like this. You perform a duality transformation. Now it looks completely different, but it might be easier. Maybe a circle is easier to solve than a square. And you might gain some insight, right? And dualities are not important because you can only map one Hamiltonian, right? You can map a family of Hamiltonians, and by tuning some parameters, one might even turn into the other, okay? And so it's interesting to see, right, when you can sort of swap these two. And the famous example when that happens is the Kramers-Monnet duality in the transversal Ising model. So I have 2 terms competing, a ferromagnetic term, Ising coupling, right, and a transverse field term. And there are 2 phases, the ferromagnetic phase and the paramagnetic phase. And because of this so-called duality, we're able to pinpoint this critical point to be at the transversal H = 1, right? Why is that? Because on one hand, we have the ferromagnet and the paramagnet. As we tune through the parameters, we reach a point where the 2 sides actually look exactly the same, right? And that's our critical point. And then when we go through all the way, these 2 things swap. right? So the amazing part is that this duality transformation actually becomes a symmetry at the critical point, right? Okay, so people have been studying how the Kramers-Wanier operation can be thought of as a non-invertible symmetry. And the funny thing is that when you try to realize on the lattice, although in the continuum we know that this should be described by an Ising fusion category, but when you try to lift it to the lattice, you find that this operator you define, which maps X to ZZ, it has a weird mix with lattice translation. And there's a bunch of work here, including some recent work by Shuheng and Nati, which try to pinpoint out exactly that there is really a mix with translation, and you really can't get rid of it. Okay. So what I want to do today is try to generalize this picture. I want to see what else, how else can I get other symmetries, which potentially might mix with lattice translation. And the idea here is sort of related to trying to get more general self-dualities. Now, this self-duality symmetry in the continuum is very closely related to half gauging. So in the continuum, you know that if you gauge some symmetry, you can come back to yourself, then that's one way to get a self-duality. On the lattice, there's some, you need to do more care because you might not come back to the same Hilbert space. There's just some subtlety, and I'll point those out a bit. And moreover, this gauging in the lattice, people usually are comfortable with gauging abelian symmetries, maybe non-abelian symmetries, but the ones that give you a self-duality are just these ones where you gauge abelian symmetries, and those just give you Tambari Yamagami. So if you want to go beyond that, you have to be able to gauge something that is non-abelian that brings you back to yourself.
Are you in compact space or non-compact space?
Am I in compact space?
I'm sorry, I meant the topic you're talking about.
Mm-hmm. I can be on a finite chain. That's totally fine.
Thank you.
Yeah. Okay. And the claim is that I can generalize this to any self-dual Hopf algebra. And for example, if the Hopf algebra is Z2, we have the duality that Z2 is related, is equivalent to rep Z2, and so the self-duality is Ising. And an example beyond an abelian group is this so-called H8 Hopf algebra, for which the representation is itself under its dual, and you can get a larger self-duality. And that has been studied by these folks recently. And basically what I want to do today is try to do this on the lattice explicitly. Okay, and the language I'll be using is closely related to using these Hopf algebras. Okay. So before I continue, I just wanted to point out a little conspiracy theory of mine, which is that there's a bunch of stuff that are really related to each other. People have been studying cluster states, the fact that it's an SPT, the fact that you can relate it to gauging, which we recently pointed out. And all of these are also related to the quantum double. In the quantum information community, people have been studying something called ZX calculus, and they're closely related to Hopf algebras. And recently, with Shuheng and Pranay, we've pointed out that ZX can be used to understand self-dualities. And that is all from the Z2 case, but what I want to do today is try to generalize all of this to the Hopf algebra. And of course, over here, people have recently generalized cluster states to Hopf algebras. And so there's all these that have been developed in parallel, but I guess now is a good time to put everything together. Okay, so here's the outline of my talk. I'm going to give you a crash course on what's called ZX calculus quickly. And then I'm going to show you how these sort of small tensor networks, when you stitch them together, can give you the Kramers-Wanier duality. And then I'll comment on the relation to Hopf algebras and how I can use this to get a self-dual sort of symmetry for the general case. Okay, let's begin. So what is the ZX calculus? ZX calculus is just based on some small tensor networks, which you glue together. The basic building block is this so-called green spider and a red spider. So the green spider, let's say that it has 3 legs. Just think of it as a GHZ state. So it's 0, 0, 0, and 1, 1, 1. It's a 3-side ferromagnet, if you will. Now, if you think of it as a map, let's say I input 0 here, then the output give me 2 zeros, right? And if I input 1, the output will be 2 1s. So as a map, you can think of it as being some sort of copy tensor. Whatever I put in, it just copies the result. Okay, so this is like a GHZ. The red tensor is the dual of the green tensor. So I can go to the plus minus basis instead. So plus is 0 plus 1 and minus is 0 minus 1. Okay. And if you wrote it out in the 0, 1 basis, what you'll find is actually it's going to add these two inputs and give you one output. So if I input j plus k, the output will be j plus k. So I'll call this the sum tensor. And it's related to the GHZ because I just perform a Hadamard or Fourier transform from this basis to this basis. Okay. Now, you don't need to really worry which one is green and which one is red because it's already Wednesday and I haven't figured out which one is for my office and which one is for the mail room. So you don't need to worry. But anyways, green, oh, here we go. Is it on there? Should I move it? I thought I was safe using Keynote. Okay. Now, the point of the green tensor, it has some nice symmetries. I told you it's a 3-state ferromagnet, right? So any Ising interaction, ZZ, will have eigenstate plus 1. So if I add ZZ on these two sides, it does nothing. And on two other sides, it also does nothing. Also, since there's a Z2 symmetry for my ferromagnet, right? If I flip all the spins, applying X on all legs, that also does nothing. For the red tensor, I just swap my rules. So Z on all legs does nothing, and X on two legs does nothing. Okay. Now, in general, you can make the so-called bigger spider, right? You can have as much as zeros and ones as you want. That's just a bigger ferromagnet. And the thing that relates the two is this Hadamard. So Hadamard changes the green to the red. That's all you need to know. And just to point out some fun examples, what is a one-leg green tensor? That's 0 plus 1, right? So it's a plus state. And what is the one-leg red tensor? It's plus, plus, minus, so it's a 0 state. Okay. And the nice thing of this is that only the topology matters. So whatever maps I write, I can deform this using, it doesn't really matter how I define this. For example, the so-called C0 gate in quantum information, you can think of it as this map. You start with A and B. The green copies A, right? And then adds A to B. So this is exactly what quantum information people call the C0 gate. Okay. There are a bunch of rewrite rules which allows you to manipulate these diagrams. One obvious one is if you have two GHZs and you connect them together, you just get a bigger GHZ. So that's obvious. There are other rules that I won't go through. This one is it will be important. I can change red to green using the Hadamard. And maybe another fun one is bialgebra, which is I can add two things and then copy them. And it's the same thing as if I copied them separately and then added them, for example. So a lot of these rules are very obvious. Okay. So that's all I need to say for ZX. Now let me convince you how to get the Cramer's one-A duality. Now before I do that, I want to be very pedantic about what I mean by Z2 symmetry. So please bear with me. So there's a distinction between Z2 and rep Z2. Secretly, they're the same, right, because they're related to the Fourier transform. But I want to be very specific what I mean. So by Z2, I will mean the symmetry which acts as X, and that's the symmetry of this Ising model, ZZ and X, ZZ minus X. And because Z2 acts, right, so it sort of adds 1 to whatever state you have. Whereas a rep Z2 symmetry, there are two irreps of Z2, right, the trivial rep and the sign rep, and the sign gives you a sign, and that's poly Z. So I want to make a distinction because that will become important in a bit. Sorry?
You choose, no?
Yes, yes, and because you can rotate into each other, you might say, oh, they're the same. But
or you fix one and then you...
Right, right. But now if you go to non-abelian, for example, G is not rep G, right? So that's why I want to make a distinction from the get-go so that we won't be confused later. Okay. So now how do I gauge a Z2 symmetry? I'm just going to claim, okay, look at these tensors. I take the green guys and I glue them with the red guys. My claim is that this gauges the Z2 symmetry. So if we look, the kernel of this map down here is a Z2 symmetry. By the way, time runs upwards. Because if I apply a product of X down here, you use these rules. X can be split into two X's, right? And then they pairwise annihilate up there. So acting on X here does nothing. And the co-kernel of this map is a rep Z2 symmetry because you swap the rules of green and red, right? So you swap what X and Z is by the same thing. If you apply product Z, that does nothing. Okay.
Can you clarify? So symmetries are just some automorphisms of the algebra observables. Mm-hmm. So what is saying? What is this? What is this thing that you drew here?
Yes, you're about to get. You might not be convinced why this corresponds to gauging. So let me convince you why that is. Okay. So using Zx, I can deform my diagram. You can convince yourself that this is actually equivalent to that. So please bear with me. I just fuse these green ones into a big green one, and then fuse this red one into this red one. Now let's interpret this as a process. So I have my input state. Let's say they're on the vertices, and I introduce some gauge fields on the edges of my lattice. Right? They were in 1 plus 1D, so edge and vertex are sort of on the same footing. I introduce some gauge fields in the state 0. Then I perform an entangler, which entangles this so-called SPT state, it's this cluster state, and then I perform a projection. So this is exactly what people think of as gauging, because you're adding a gauge field, you couple them together, and then you perform projection to enforce the Gauss law, right? In the way of thinking in terms of field theory, right, the adding gauge field does nothing here. You can do it for free in the continuum. But when you sum over these gauge fields, you always have to add this factor, right, which you could think of it as a Fourier transform of this one form, but it's exactly the term which is the response of this SPT. You have a Z2 symmetry and a dual Z2 symmetry, right? And then the sum is this projection.
Can I also ask a follow-up question on Anton's question? So this operator you write on top,
yes.
What does it act on? Because I shouldn't think of it as acting on the Hilbert space, right? Because then I don't get an operator as a kernel, but a subspace.
Correct, right? I'm going to a different, so by gauging, you go from the original Hilbert space to a dual Hilbert space. You're not back to yourself yet. That's perfectly correct. I'm going to fix that in a bit.
Okay, I will ask you again.
Yes, Nati?
First, the question I already asked before. Are you in compact space with periodic boundary conditions or not?
Yeah, I can do this in compact. So there's dot, and then it wraps around.
But then you have to worry about what's going on at the last point. Where you.
Oh, yes. I'm on periodic boundary condition for a finite.
Okay. The other thing is that there's an important distinction between the continuum expression you wrote and the lattice, where when you gauge a Z2, in the continuum there's always what is known as a quantum Z2 or dual Z2.
Yes.
But on the lattice you have to tune some parameters for that. Are you doing that or not?
So the dual Z2 comes in the moment I introduce these gauge fields. So these gauge fields has a rep Z2 symmetry. Right? I initialize them in the 0. So they have a prod Z symmetry.
Right, but then there are more terms that you can add to the Hamiltonian. I believe this will be red X's. I'm not quite sure I'm using the colors in the XZ correctly. There are more terms you can add to the Hamiltonian that break the symmetry. Maybe you don't want to add them.
Perhaps. I'm just doing something very specific here. So yeah, I need to think about it, but yeah, I can ask you more afterwards. Okay, yeah. What I'm just to convince you is that I was trying to move my mouse already. That's back. Oh, okay. This thing performs the gauging. So you input something with a Z2 symmetry, it gets killed, you get a dual rep Z2 symmetry on the other side. Okay. So, right. So coming back to the question, it's not the same Hilbert space. We need to fix it. How do we fix it? And there are 3 steps here. I think it's actually very similar to what Kevin tried to say yesterday. This is my interpretation of it. You first perform gauging. So you go from the Z2 Ising model. After you apply this gauging step, you go to a rep Z2 Ising model on the dual lattice, right? Then now you need to fix it. The first thing you need to fix is you applied Hadamard. That changes rep Z2 back to Z2, but you're still on the dual lattice. And then the last step is you perform this half shift, so you come back to Z2 Ising again. So this duality thing is not just gauging on the lattice. You need to be careful because you have to turn from rep Z2 back to Z2 and also this lattice shift. Now the nice thing about ZX is that I can make this picture symmetric. I can push Hadamard down, change this to green, and now you can see the top and bottom actually look the same. So So the kernel and the co-kernel is now both Z2, not the other side is not rep Z2 anymore. Okay. Let's see. So you can also use ZX to compute the fusion rule. Let me not go through this, but let me just show you that in principle, using these rules, it is possible to do this computation. Okay. So now let me go to the Hopf algebra. So in the most general case, where we don't have co-commutativity, in the most general case, we have to worry about the order in which we multiply things, right? So we don't really have this luxury of like moving things at will anymore. So we have to be more careful. But in the mathematics literature, this sort of, the fact that you can fuse these green things into one big blob is actually secretly this notion of having an associativity condition and this sort of unit condition. So it's just telling you that green things can be treated as one big green thing as long as you keep order of the order you multiply them. Okay. So this is something called a monoid. And in a Hopf algebra, you just have one green guy and one red guy and together. And the only other ingredient you need is something called an antipode. And in the Z2, we didn't see that. But the antipode is sort of, in the group case, just inverting every group element. And this is just keeping track of that. And the Hopf rule just is a modification where you have to add the antipode here. It's just saying if you split a thing into two, right? You invert it and you multiply back together, you always get identity. So it doesn't care what the input was, and the output is always 1. Okay. And because antipode inversion sort of swaps, when you invert, you have to swap the order. That's why you have to swap the legs here. So I need to be very careful about how I swap the legs in the general case. For example, let's gauge G symmetry. Now the green tensor will just be copying G, right? And the red tensor will be multiplying G and H to get GH. And we have this antipode map, which maps G to G inverse. And the map looks very similar. I have this green and I have this red. I just need to put antipode on half of them. And what this does is you copy G, right? You invert one of them, and then you multiply the result. And so this is sort of going from, in some sense, the spin configuration to the domain wall configuration. You're just computing the difference between the two for every pair, right? And you can see that the symmetry on this side is a left G symmetry, because if I multiply G on every side here, the output state is still the same. So the symmetry is left multiplication. Now the dual symmetry is rep G. And what does that look like on the lattice? It looks like I copy every state. I put that so it's defined for each representation. I copy my state, I put it into the representation, and then I compute the trace. So you can also view it as you copy your state, you multiply them all together, and then you compute the character. So that's how the rep G symmetry acts on the lattice. Now, so finally I can tell you what is ZX calculus in a mathematical framework. And this has been discussed in these sort of math papers. For a usual Hopf algebra, you have a multiplication, which is this red guy, this co-multiplication, which is this green guy, and an antipode. But you notice that in my diagrams, I also had the green one was upside down, right? So, well, what does that mean? I also have to have a second Hopf algebra, where my multiplication is the green guy, my co-multiplication is the red guy, and with the same antipode. And together, they have to satisfy some consistency relation. For example, the green guys have to interact in a nice way such that the order doesn't matter. And this structure is exactly called a Frobenius algebra. So together, all this structure together is called a Frobenius Hopf algebra. So that's what is known in the math literature. Now, this can be defined actually for any Hopf algebra. But if the Hopf algebra is self-dual, you have an extra structure, which is you have something called a Hadamard, or Fourier transform. And it allows you to swap between the red guys and the green guys. Now I have to worry about order of multiplication, so there might be some swap of the legs here, but this is how it works in the general case. And this only exists if if your Hopf algebra is self-dual. Okay. So, yes.
Is this the same idea of Frobenius algebra that people use to gauge in the continuum for like non-invertible symmetries, or is there a difference?
The Frobenius is just this part, but I actually need this whole Hopf and Frobenius interacting in a particular way for this this setup.
You think there are more conditions?
Possibly, yeah. I'm not sure, but yeah.
Okay.
Do you have some comment?
I guess for any finite dimensional Hopf algebra, you can define the Frobenius structure and to define this Frobenius algebra. But it's different from the you gauge algebraic objects in the RAP-H.
Okay, so finally, this is actually, I already did most of the heavy lifting, so actually this is now pretty simple to state. I basically take my gauging map. It's the same with the antipode inserted correctly. I do a Hadamard. Just for conventions we choose, this has to be Hadamard dagger. So Hadamard doesn't square to 1 anymore in the most general case. It actually squares the antipode. And then I perform a shift. And then now, again, you can push the Hadamard down, and then you can get this, and you can make this now look symmetric. And now you can see the importance of the dagger here. It's because if I flip the picture down, I need the picture to look the same. So the dagger becomes undaggered, and that's why you need to stagger it like this. And now the nice thing is that this map has both the kernel and the co-kernel are so-called rep-H star symmetry. So this is this generalization of the group case to an arbitrary Hopf algebra. And you can compute the fusion rules similarly up to the translation. What you'll find is that you'll just get back the action given by the regular representation. So it's you sum over all the irreps weighted by the quantum dimension. Okay. So in some sense, this Kramers-Wanian generalized version is sort of the square root of the regular character. Okay. So what Hamiltonian has this symmetry? We can write down a similar Ising model based on ZZ and X. Now there are arrows on there because I had to worry about whether I multiply from the left or from the right. But the two limits are easy to state. For the paramagnet, this is the ground state of this, you just get a product state. And the product state is just this green dot. It's just a product state of this green dot here. For the ferromagnet, you just connect all these up, and that's the ground state. This is a big ferromagnet. And just for a sanity check, if we reduce it to the cyclic group case, this will reduce to the well-known Klotz-Potts model, depending on the parameters you choose here. So you're free to tune these parameters for each irrep separately. Okay. So this is just the clock model. Now, interesting, let's go beyond the group case. What happens if I define this for my H8 Hopf algebra? Now you need to define what are these x's and z's properly. The x is probably more well known. You can multiply something from the left, or you can multiply something from the right. But for the generalized z, you have to co-multiply, which you can do also from the left or from the right. And this is how it's defined. Now for rep H8, there are 5 simple objects, and you can sort of think of it as this subcategory of Ising. And so the interesting thing is the Hamiltonian has 5 ZZ terms and 5 X terms, which you can tune, right? At the self-duality point, you have to match them to be equal, but there's still 5 parameters that you can actually tune. Okay. And an interesting thing is because this case is not a group anymore, the green dot, in the group case, the green dot always copies. But in the most general Hopf algebra case, it does not copy anymore. And so it turns out that the ZZ term, the Ising term, if you define it for the first 4 sign reps, it's a diagonal operator. But for this guy, it's actually not a diagonal operator. So the Ising model, it's not, the Ising term is not diagonal anymore, interestingly. Okay, let me just summarize. So what I did is I showed you an operator which gauges rep H for an arbitrary Hopf algebra. So I didn't have time to walk through the gauging process, but it's basically the same idea. Based on that operator, you can think of it as adding ancillas, coupling together, and then forming a projection, and that realizes this explicitly. And when your Hopf algebra is self-dual, I can define a self-duality symmetry, right? And I can define a generalized Ising model which has this self-duality at the critical point, or at the midpoint. We don't know if it's critical yet. So it'll be interesting to work out the phase diagram for this Ising model, right? It's a 1D chain. You can use DMRG pretty easily, and that's what we plan to do next. So it'll be interesting to see whether there's a critical point or is there some intermediate phase in between. It'll be interesting to see for here, I restricted everything to just usual gauging. I actually don't know how to do twist gauging in this language of Hopf algebras. Maybe someone can tell me how to do it properly. Maybe you have to use quasi-Hopf algebras. I don't know the answer. So that's one thing I want to think about more. Another thing we can generalize is I assume the local Hilbert space is the Hopf algebra itself. And but in principle, we can have it for a lattice model where on a more general Hilbert space, I just need to change the multiplication to some action. And interestingly, this rep H8, because I defined it initially, does not mix with translation. But there are other models for which rep H8 mix with translation. It's like in two Ising chain. So they are realized different in the UV. And I can gauge this rep H8, but I don't know how to gauge this rep H8. So it would be interesting to see if there are any differences on the UV. Yeah. Okay, I'm done. Thank you.
It's a very nice talk. Do you know what symmetry governs this potential transition? Like in the Ising, it's Z2, and in these...
It's rep H.
It's just rep H. Yes. And so do you know what between which gap phases it's...
So the paramagnet is just the preserved state, and then this one is completely broken. So for example, for rep H8, this will be 5-fold degenerate, and this will be...
Are these all the gap phases?
No, they're not.
No, they're not.
But you can tune these.
You can tune, and then you can also go to other critical models.
Right. This does not, this, for example, will not give you other SPTs. You can, you can also write down different other models, right? For example, if I wrote this for Ising, I won't get the cluster state. I need to do some more work. There are more terms I can add, actually. Yes.
Okay. Thanks.
Yeah, so a long time ago when this subject was in its infancy, like around early 1980s, there was a way figured out how to do duality transformations for non-abelian spin models, which is, the problem is that the kink operators don't have local commutation relations. So you can do something formal, but it's kind of useless because they won't commute with each other. If you make a rotation in a non-abelian group, then it's not going to commute with a line of rotations at different points. But the way to solve the problem, there are a couple of ways. One was by Belisar, where you found that if you have a solvable group in the sense of Galois theory, you could actually rewrite the spin chain as an abelian model. And then, of course, you could do it in a straightforward way. You could write different operators. There's another way of doing it if you have the symmetric group. What you can do is you can write down operators which make the kinks, but actually do have local commutation relations. And I don't know if there's any connection with what you've done. You have these half algebras, and they aren't abelian. So my question is can your kink states, do your kink states have a local set of commutation relations on this Hilbert space?
I just want to understand that nomenclature. By kink, you mean some defect of the symmetry?
I mean the operator that creates the dual spin, which, I mean, you constructed it in your talk, but essentially it's always something which is some local operator times something on a half line.
I guess you're saying that, for example, Z maps to a string of Z on the other side.
Exactly, right. And so those things will commute naturally in an abelian theory, but if you have a non-abelian symmetry, they don't. They won't have local commutation relations. So the trick is you have to really map your model into something which is not truly non-abelian, which can be done for certain kinds of problems, like the symmetric group is one example, the solvable groups are another example. And so the idea is to pretend you really have an abelian model and write it in that way. But you have this half algebra, and you never actually, I mean, I think you allude to it by doing your mapping, but you never actually write down the kink operators. And I'm wondering if your kink operators, I mean, they should have local commutation relations, but I didn't really see it in your talk, and I'm wondering if you have any insight into that.
I guess all I can say is there are these generalized X and Z's that you can define, and you can work out their commutation relations. They're not very simple.
Right.
But yeah, I'm not sure I have more to say at the moment. Maybe I can ask you more later about.
Okay, I mean, it's just, can you write down explicitly the operator that corresponds to the dual Z is what I'm saying. Not the product of two Z's, but just one. That should be a kink operator.
I think it should be possible, but I need to think more about it. Yeah.
I think another point is that this ZZ operator and X operator in the expression that corresponds to the like co-commutative elements in the Hopf algebra.
Yeah.
Yes, that's a good point.
Some particular set of the Hopf algebra.
Don't see how that answers my question, but that's probably my own ignorance.
Yeah, the single Z's will commute in this case, right? Because it's a, yeah, I need to think more, I'm not sure.
Yeah, I think we need to think more about this relation. But the symmetry operator for the Hopf algebra, they correspond to the co-commutative elements in the Hopf algebra.
They correspond to what?
Co-commutative.
Co-commutative. Okay, so you're saying that they should commute locally?
We need to check.
Okay.
Yeah.
Thank you for the nice talk. In the H8 Ising model, then you do test this duality symmetry, right? And so, therefore, does that make your category of symmetries larger? So you have this rapid H and the duality defect. Do you know what that forms altogether?
Yeah. I mean, in the continuum, it's these papers that I mentioned here. They studied what happens if you self-gauge the whole rapid H8, and they called it this, but it's basically you add one more thing to your fusion category, and they just gave it a name. But
okay.
Yeah, this is whatever generalized Ising is this, yes.
Can I ask a related question? So in the continuum, okay, so in general, when you do the G2 extension of RAB-H, there are multiple options. Do you know which G2 extension you get specifically?
This one is the fully gauging one, if it does that.
So, for instance, for the RAB-H8 case,
yes.
So for fully gauging it, so there are 8 different G2 extensions.
Oh,
in
like,
the temporal megamic is like bi-character and proportional indicator.
Right, you mean like twisted gauging, yeah. I guess
no, all these are the same gauging, but there can be different. In the temporal megamic case, you just gauge the abelian group without any twist.
Yeah.
But when you do the G2 extension, you have choice of bi-character and proportional indicator. Right. So there is a generalization of this for general RAB-H. So do you know which one you get, or possible G2 extensions?
It's a good question. I thought for Z2 times Z2, like it boils down to whether you have some co-cycle and some twist or not. Does that, maybe I misunderstand.
If you do the twist, you get something even more different.
This one is just the one where there's no twist.
Yeah, without twist, with twist you will get some other extensions, say G3 extension and so on, but yeah.
Yeah, without twisted, there are like 4 extensions of the Z2 times G2, right? And in this case, there are 8. It's basically, it's like the F symbol choice of the resulting fusion category after you do the Z2 extension. Maybe Datran can say something more.
Okay. Yeah, so the Z2 extension of this RAB-H8, there are 8 different gauging equivalent F symbols, and the 2 of them correspond to the bulk ion permutation symmetry, and 2 of them correspond to the fractionalization class of the Z2 symmetry in the bulk, and another 2 is FS indicator. So my naive guess is, so first of all, the FS indicator is +1 in our case. But if we want to really match the F-sim fusion category, we need to construct the defect and then calculate the F symbols from the symmetry defect.
I guess the bi-character part should be very visible here. Wait.
I think so.
At least the bi-character part should be very visible. That's like you do the duality, you have the duality interface, and then you just look at the symmetries coming from each side, and you ask how do they commute with each other on the interface. And that should be very directly calculable on yours.
Probably, yes. We haven't done that yet. We were just working the Ising model this Monday, so everything is very fresh.
Yeah, so one question is, so there are some cases like if you want to end up with the self-dual, you can gauge just an algebra object instead of gauging the full thing, right? Like, how should I think of this adding new?
Right, I don't know how to do the most general case, but if you give me a Hopf subalgebra, then I know how to partially gauge. But for a general algebra object, I don't know how to do it in this framework yet.
I see, okay, thanks.
Yeah. So for a group, I can gauge, say, any subgroup, right, because that's a Hopf subalgebra.
Yeah, I just wanted to comment on the previous question. So it turns out that for general groups, there's different dualities, and the dualities are labeled by another module, and all these different kind of modules are needed because you have to act with your symmetries, both of the original model and the dual model, on this duality defect. And this changes all these different dualities into each other. So they're effectively equivalent because you can turn them into each other by acting with your symmetries, either in the original or in the dual model, but these are different dualities.
Like add with an SPT entangler on both sides.
No, that's even different, indeed. And that's the answer to your question about twisted gauging. That is actually somehow extra than, yeah, that's how you would do twisted gauging.
Okay.
For having a self-duality, one necessary condition is that you have an algebra object in the fusion category, such that the dual fusion category is also isomorphic. So is it also sufficient for finding a self-dual half algebra, or is it more stronger? Because that enables you to realize it on the lattice. So I was wondering how much of it is specific to this.
I feel that could be stronger because what you're doing is already more general than the gauging algebra object. Is already more general.
Gauging algebra object, it might not be self-dual. So let me just at least assume that the dual category is the same. I'm saying, would that be sufficient for finding self-half algebra? If not, because half algebra is more data than just a symmetry. I'm saying that finding a self-dual half algebra, how much it restricts the symmetry and the algebra object that you're gauging.
Yeah, that's a good point. Yeah, the point of using all of this is because, okay, there's a big literature on half algebras and people study all these self-duals. So it just gives us a bunch more examples that we can just churn out, having this, by doing it through this formalism. Yeah. So it's sort of, yeah, I don't know how to do the most general one. Yeah.
But this is also stronger than just assuming that rep H8 is the same as rep H star, right?
Yeah, we know it's equivalent, and you actually have to find the map, and that's non-trivial. Like working on what this Hadamard gate is quite non-trivial, and we spent almost a month figuring out what the right mapping is and what is the normalization. Yeah, it's pretty non-trivial.
Okay, so is it just to move to the coffee break? So let's take it out the game.